Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Today, inshallah, we will talk about a new session, session 13, about classification. The first thing is to know what classification is. Classification is about learning how to make predictions from past examples. And the best way to understand what classification is by showing some applications or some examples of classifiers that we actually see in our daily life. The first application is detecting fraud in online transactions. So we can build a classifier that, given an online transaction, it detects whether it is fraudulent or not, whether it is fraudulent or valid transaction. How can we build a classifier to do that? We show the classifier examples of valid transactions and examples of fraudulent transactions. And the attributes that can be helpful in detecting whether the online transaction is fraudulent or not is something like the amount of money that we use, the type of the things that we are buying online, the address of the credit card, the location from where we are making the transaction, and so on. Another example that we also use and we are very familiar with is spam filtering. So all of us in our email clients, they use spam filtering. So for any incoming email, we want the classifier to detect whether it is spam or non-spam. And we train that classifier by showing examples of spam emails and examples of non-spam emails so that the classifier can build a model that can distinguish between these two types of emails. Another example is what we call sentiment analysis. So given a review like that, I want a classifier to tell me whether this review is positive or negative, whether a customer here likes the product or dislikes the product from just the text in the review or in the comment. So we saw that all the time in Amazon or eBay and so on. Another example is friend recommendation in Facebook or in Twitter. So here we build a classifier to tell us whether, for example, this person we should follow or not. Okay, so the classifier can say whether this can be a good candidate to be followed or not for the specific user. So all of these are examples of classification. So let's see a demo on two data sets for classification. So the first example is about chronic kidney disease. So this dataset has multiple attributes or features. So each column, each row here is about one patient, and the columns are measurements from blood tests for that patient. And you will see at the end of the dataset the class column. If it's 1, that means that this patient is diagnosed by this kidney disease. If it's 0, then he or she is not diagnosed with this disease. So if we go by the class, we'll find that this dataset has 115 patients who were not diagnosed with this disease and only 43 who were diagnosed with this disease. Now, we want to build a classifier that can detect whether a new patient can or should be diagnosed with the disease or not, based on his or her measurements of the blood test. So let's explore how we can do that manually first before we actually study one example of very well-known classifiers. So let's say that we want to look into two attributes from this dataset, the white blood cell count and the glucose value, and we will plot a scatter plot with these two attributes. Now, if we look at this plot here, we'll find that it is really hard to find a way or a rule that can tell us whether any of these points, which actually corresponds to one patient, is or should be diagnosed with the disease or not. Here, the blue dark ones are the ones who were not diagnosed with the disease, and the gold ones are the ones that were diagnosed with the disease. So let's try two other attributes. the hemoglobin and glucose again and see if that will be helpful. Now in this case, it is clear that it is easy actually to separate or to distinguish between the patients of class 1 from the patients of class 0. So if we know the value of the hemoglobin and the value of the glucose, then we can say that if the value is in this area, then we should predict that the new patient belongs to class 0, which means that he or she will not be diagnosed with the disease. Otherwise, it seems like we can predict that he or she will be diagnosed or has actually infected by the disease. So we can actually write a classifier manually to predict for any new patient, given the information from the blood test, whether the patient is diagnosed with this disease or not. To do that, we will get the maximum value for the glucose attribute, so this value, okay, and we'll get the minimum value for the hemoglobin, which is here, something here, and based on that, given the new hemoglobin and glucose values of the new patient, we can decide whether he will be diagnosed or not. So to get the maximum value for the glucose, we will focus on the group of patients who were not diagnosed with class 0. We'll get the column glucose and get the maximum of it. Same thing with the hemoglobin, but here we will get the minimum because we need to get the minimum of the hemoglobin and the maximum of the glucose value. So getting these two values, now we can do the classification. We can say that given a new hemoglobin value and glucose value, if the hemoglobin value is less than the minimum, so which means that it is at that side, or the glucose is above this value, so if it's below this value on that axis or above this value on that dimension, then we will return 1, which means that this person will be diagnosed with the disease, like all of these yellow or gold points. Otherwise, we will return 0. So that's the classifier. We build it manually by looking at the data and by manually trying to find the pattern in the data that can help us distinguish between these two classes. Now let's try our classifier. Let's classify 15 and 100. So 15 is somewhere here and 100 is here. So this patient should be diagnosed, predicted to be of class 0. Okay, so that means that he will not be diagnosed with the disease. So that's what we get here. If we classify 10 and 300, this is 10 and that's 300. So somewhere here, it should be class 1. Okay, so that's based on the manual classifier that we get. Of course, we want to automate something like that, but that's just a motivating example to show how classifiers actually work. Another example is about banknotes. So the paper money, we want to know whether one banknote is legitimate or not. So let's look at the data set. So the data set here has 4 attributes. These attributes are features or attributes that were extracted from an image of the banknote. We don't worry much about how these values are computed, but let's say that we have these 4 values for each example of a banknote. And as usual, we have the labels, which is the class column here. So all of these are zeros, which means that they are okay. And the ones are the not legitimate banknotes. So here we have 762, which are okay, and 610, which were not legitimate. Now let's do something similar to what we did in the previous example. Let's look at 2 attributes together and see if we can find a pattern in the data that will help us distinguish between the 2 classes. So we'll try wavelet var and wavelet curt here. These are the first and the third columns here. we will see that it is not easy to find a way to distinguish between the two classes here because they are mostly overlap. Even if we said that in this area it is of class 0, but still there are some of the points here that are on that side. Let's try two other attributes, which will be the skew and the entropy, so the second and the fourth. So we'll draw a scatter plot for these two attributes. Again, it is not easy to distinguish between the two classes here. They are also overlapping. So it seems like two attributes at a time might not be a good idea. Let's try three attributes together. Okay, so also don't worry about what we are doing here. It's just a scatter plot, actually a 3D scatter plot of three of the attributes, the skew and the bar and the curve. Now let's look at the 3D graph. Now surprisingly, with the three attributes, we found out that they can be distinguished from each other. They are not very much overlapped. So it seems like looking at three attributes, and maybe in other examples or other cases, more than three attributes will be very helpful. So humans can look at two attributes at a time, maybe three attributes at a time, as we saw in this example. We might find ways easy in these dimensions, but more than that, we actually need help from systems. So we cannot actually visualize more than three dimensions. It is really hard, but systems will not have any problems in doing that. So let's see how we can actually build a classifier automatically. So let's get back to the slides. And before we do that, we will talk about one more example of classification, which has been done in Google Science Fair in 2012. So in 2012, a 17-year-old high school student won the best Google Science Fair model by building a breast cancer classifier with 99% accuracy. There was a competition for classifying benign cancer from malignant cancer from images, and the student, the high school student at the time, managed to build a classifier with 99% accuracy, which means that it has for 100 cases, she got 99 of them correct. So the classifier makes 99% of its decisions correctly. That's what we mean by 99% accuracy. So here's an example of a benign cancer, and here's an example of malignant cancer, and she was able, by this very high accuracy, to distinguish between the two from all of the different examples, the testing examples that was used in the science fair. Let's see a demo about this. So here is the data set. So the data set, of course, the images will be represented by, again, some attributes. Okay, so we don't care much about the meaning of these attributes now, but we know that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 attributes from the images, and we have the label for each image. So each row here is one image, and we want to detect whether it is benign or malignant. So if we go by a class, we will find that we have this distribution of the two possible labels. Now let's look at the data. Let's look at two of the attributes together. And because these attributes are integers, you will find that the figure here is not very friendly because it shows overlapped points on top of each other. So we actually don't know whether this is just one point or not, because both attributes are of similar ranges and integers. So we cannot tell from that graph whether we actually have one point here or more. So what we do is to add some noise to the points here so that we can see them, just random noise. And again, we don't worry about the code here, but we will just add some random noise to each point so that it won't be exactly at the original point, so that we can know, or we can see areas of multiple points where the points overlap. So we'll do that. We would see that for example, now of course this is different from what we saw before. Here, for example, there are multiple points, there are multiple points here, and so on. So instead of just one point here that is overlapped with other points, we see a cluster or a group of points to show us how many, or whether we have so many points here or not. From that graph, again, it's not very easy to find a manual way to classify here. You see here there is an overlap, here there's an overlap, here there are some overlapping points, so it's not very easy actually to distinguish between the two classes. So that was just to show you some real examples of classification datasets or classification problems. In the first one, we saw that it was really easy to do the classification. In the third one, it was not that easy. We had to use more than 2 attributes. Here, it's not clear whether we can build a nice or perfect or accurate manual one or not, so we will need to find an automated way to build a classifier. So let's get back to the slides, and now we'll talk about classifiers. Now, how can we build or we train a classifier? So the classifier is used in this way. After we build the classifier, we are given attributes of one example, like the attributes that we saw in the 3 datasets that we just studied. And the classifier job is to predict the label of that example. Okay, so online transaction with all the attributes of the online transaction, the decision will be whether it is fraudulent or not. An email with all the words in that email, we will predict whether that email is spam or not. Now, how can we get that classifier? Of course, we will not do a manual classification, or we will not by ourselves look and find pattern in the data manually. Okay, so we'll need to find an automated way to build such a classifier. So this automated way called training. Okay, so we train a classifier so that when in the future it sees an example, a new example that was not seen before, it will be able to predict the label for that example. We will assume that we have a population of examples, okay, population of online transactions, population of emails, and so on. And we will take a sample from that population. Okay, hopefully it will be a random sample that is representative of that population. Now, in order to train the classifier, we need labels for this for the examples in this sample. Actually, for each example, we need the correct class for that example. So if we are building a spam filter or spam classifier, then we need a list or a set of emails that are spam and a set of emails that are non-spam, so that the classifier can learn from these examples how to distinguish between spam emails and non-spam emails. But actually, we split this sample into 2 sets. One set is called training set and the other is called test set. So the training set is used to train the classifier to learn patterns from the data so that the classifier can distinguish between the classes of the data. Now, what is the purpose of the test set? The purpose of the test set is to test the classifier after being trained in order to evaluate the performance of the classifier, or in other words, the quality of the classifier or the accuracy of the classifier, as we will see later, inshallah, in this session. So in the training set, we model the association between the attributes and the labels. We try to find relationships between the attributes and the labels, which means that we will learn patterns from this labeled data. But the test set will be used to estimate the accuracy of the classifier. Now the example classifier that we will study inshallah in this session is called nearest neighbor classifier. And the idea of the nearest neighbor classifier is very easy. So what is the idea? The idea is that given an example that we want to predict the label for, we will try to find in the training data an example that is the most similar example to the given example. So we have training data here. We are given a new example. So we will take that example and we'll try to find in the training set the most similar example in the training set. So one example that is very similar to the example that we saw here. Now, what we will do with the most similar example is that we look at the label associated with that example. So actually we will check what is the class of that example, and then we will predict that the class of that example is actually the class of the example that we found to be most similar in the training set to that example. Let's see a concrete example here. Let's say that we are building a nearest neighbor classifier of emails. So we will get some labeled emails. Some of them are spam and some of them are non-spam. Now we are given a new email and we want to predict whether this email is spam or not. So we will get attributes from that email and we will try to find here in the training set one email that is very similar to this email. Now, if it is very similar to that email, most probably these should be of the same type or the same class. And that's exactly the idea behind nearest neighbor. That the most similar example that we found in the training set, it has of course a label. Then the label of the example that we want to predict, its label will be exactly the same like the example that we found in the training set. So the label or the class of the example of the most similar example here in the training set to this example will be actually the predicted label for that example. Okay, so that's the idea of the nearest neighbor, and as you will see later in the session, inshallah, we can generalize it to be k nearest neighbor, and we will talk about k nearest neighbor later, inshallah. Now let's talk in more detail about nearest neighbors. As you saw in the previous slide that we talked about the most similar example to a given example. Another way of computing similarity between two examples is to compute what we call the distance between the two examples. So if the distance is very large, then the two examples are not similar. If the distance is very small, then they are close to each other and they are very similar to each other. So how can we compute distance between two examples or 2 points? Let's say that the example in our dataset has just two attributes, x and y. So one way of computing the distance between two examples, each has two attributes, is to use the Euclidean distance. So we get the difference in each attribute. We get the square of the difference in each attribute, and we sum them and we take the square root. That's the Euclidean distance. Even if we have more than two attributes, like 3 attributes, we can still use the same idea of Euclidean distance, but here we will get the square of the 3 differences of each attribute, and sum them, we get the square root, and so on for more attributes. Now, when we deal with distances in a table, we need to deal with the rows of the table. Okay, so each row will contain the data for one individual or one example. In order to get a specific row, we can use the row method from the table T. So we'd say row I returns the ith row of table T. Now, if we want a specific value in that row, we can access it through the item function. So row I dot item j is the value of column j in row I. Now, if we want to get the an array of all the values in the row, let's say that all the values are numbers, then we can use the array function in NumPy given the row, it will give us back an array of all the numbers in the row. So if we want to loop over all the rows, we can do something like that. We can say for row in all the rows, t.rows will give us all the rows in the table T. Now we can access the row here, we can access the J item, or we can convert it into an array or anything that we want to do with the row. Now let's see a demo on distance. Let's see how we can compute it. So here is a function that takes 2 points here and returns the distance between these 2 points using Euclidean distance. So let's assume that these are arrays. So we will do element-wise difference. Okay, now this is an array, but the array has a difference between the corresponding attributes. Now we will square each element, so this is again element-wise squaring. Then we sum over all the values in this array and we take the square root. So that will be the distance between the 2 points. Now if we want to generalize that to rows, we can get the row distance. So the row distance, the only difference between this and that is that we assume that these are rows in a table, so we have to convert them into an array before we compute the actual distance using this function. Now let's try with the patients database here, the breast cancer database that we got here, the patients from the breast cancer data set. Let's try to get some distances here. So first drop the class column, because the class column is not, it should not be used in computing distance between examples. Now we can compute the row distance between row number 0 and row number 1. So let's do that. This gives us 11.87. So this number now indicates how similar these two examples from each other. Remember, in nearest neighbor, we need to know for a given example which example in the training data is the most similar one. Now, how can we use the distance to get the most similar one? It will be the least distance, right? So if the distance is very small, then this is the most similar one. So it seems like these two examples are not that similar because the distance here is not very small. Let's try the distance between 0 and 2. We'll see that it is 2.23, so that these two examples are more similar than these two examples. Okay, so actually example 2 is more similar to 0 than example 1, because the distance between example 2 and 0 is smaller than the distance between example 1 and 0. Let's try now the example by itself. What should we expect the distance to be? If I want to compute the distance between the example and itself, of course the example and itself is exactly similar, so the distance should be the minimum distance that we can ever get, which is of course 0. Okay, because here everything is 0 and the square root is 0, the square is 0, the sum is 0, and square root is 0, everything is 0, so we will get 0 here. So that's how we can compute the distance, and by that we will end our lecture today. Inshallah, we'll continue talking about classification in the next lecture. Assalamu alaikum wa rahmatullahi wa barakatuh.